Newton said in his statement that force is inversely proportional to the square of the distance between their centers. How did he come to know? He came to know with the help of Kepler's third law. How did he understand? Let's see this. He considered sun and a planet, and the mass of the planet was considered as small m. Now, there is a distance between their centers that was denoted by small r, which is obviously the mean distance. Now, we know that this planet will revolve around the sun, and when it revolves, the velocity with which it revolves is called as the tangential velocity, denoted by small letter v. We also know one thing. We know that for a planet to revolve around the sun, gravitational force is required, and we know that gravitational force is also called as the centripetal force. There's a formula for centripetal force. The formula is F is equal to mv square upon r. This question can also be asked as a 1-mark question. State the formula for centripetal force. There you go, mv square upon r. This is equation number 1. Now, when this particular planet revolves around the sun, can we say that it is moving along the circumference, right? Now, since it is moving along the circumference, we know that the distance covered will be actually equal to the circumference of the orbit, right? And what is the formula for circumference of a circle? We know that the formula is 2 pi r. And we also know that the period of revolution or the time of revolution is denoted by capital T. Now, we know that we have a formula for speed or velocity, and we know the formula actually is distance upon time. We cannot actually say velocity, we have to say speed. Now, speed is equal to distance upon time, and we know speed is denoted by small letter v. Now, what we'll do is, since we know that the distance travelled over here is nothing but 2 pi r. So, instead of distance, we write 2 pi r, and instead of time, we write capital T. So, we get 2 pi r upon capital T. This is equation number 2. Now, we have equation number 1 and equation number 2. So, what do we do now? We substitute the values. Now, we'll substitute the value of v in equation number 1. So, what do we have over here? We have F is equal to mv square upon r. We just have to substitute the value of v square. So, what we'll do is, we'll keep F, m and r as it is. So, let's write F is equal to, we'll write this m as it is and r as it is. What do we need to substitute? We need to substitute the value of v, that is 2 pi r. But here we have v square, remember. Since there is v square, we'll write 2 pi r upon t, the whole square. Writing the whole square is of utmost importance. This is the important step, remember. Now, what we'll do is, we'll open this bracket. So, when you open the bracket, you know that this square goes to the numerator as well as the denominator. So, we get 4, that is the square of 2, pi square, r square upon t square, and m and r remains as it is. So, what we obtain is m4 pi square r square in the numerator, and we have t square, right? So, this t square and this r will actually come together. So, we get t square r or rt square, whatever you want to call it. Now, after doing this, we know that the square and r will get cancelled. So, what remains over here is m4 pi square r upon t square. So, this is the equation that is left. Now, just try and recall something. Kepler's third law, the formula for Kepler's third law is t square upon r cube is equal to k. Do we have a t square over here? Yes. But do we have a r cube? No, we have r. That means we need r square. So, what we can do over here is, we can multiply and divide by r square. So, by multiplying the numerator and denominator by r square, what we do is, we write this entire equation as it is. So, we write it as it is and into r square upon r square. Now, this r and this r square will now become r cube, and t square r square will get combined. So, what we have right now is 4m pi square r cube upon r square t square, or you can say t square r square, whatever you want to call it. Let us take this step forward. This is step number 3. Now see this very carefully, right? Now, what we have over here is r cube upon t square. But do you remember Kepler's third law, or the formula for Kepler's third law? The formula was actually T square upon R cube. So according to Kepler's third law, the formula is T square upon R cube is equal to K. But what we have over here is we have R cube upon T square, which is nothing but the reciprocal. So R cube upon T square will be actually equal to 1 upon K, since it is the reciprocal. So right now we have to substitute R cube upon T square in this equation, and everything else remains as it is. So we'll substitute equation number 4 in equation number 3. So F is equal to 4 pi square upon R square remains as it is, and we know R cube upon T square will be equal to 1 upon K. Now, in the numerator, we have this entire term multiplied by 1. So anything multiplied by 1 will be anything. That means this term. So we get 4 pi 4 m pi square upon R square into K or K R square, whatever you want to write. Now what we'll do is we'll rearrange this. So after rearranging equation number 5, what we'll do is we'll try and separate the constant and we'll try and separate the variables. Now, what all are constant over here? 4 is just a number. So 4 is a constant. Mass of the planet does not change, so that is a constant. And pi is 3.14, again that is a constant. And K itself is a constant. So what remains is R square. So we write 1 upon R square. So that means since 4 m pi square upon K, all these things are constant, right? Now since they are constant, what we get over here is F is equal to constant into 1 upon R square. So this is what we write. So F is equal to constant into 1 upon R square. That means whenever the value of R changes, only then the value of F will be affected. The constant will not change, that means force will not be affected because of these factors. So this is how we came to know that force is actually inversely proportional to R square. So this is how Newton actually realized that force is inversely proportional to the square of the distance between their centers.